This is the first lecture in a series of videos on undergraduate level quantum computing and quantum information. So the idea is to present an introduction to quantum computing in a way that doesn't assume much knowledge of quantum mechanics and is broadly accessible to a wide range of backgrounds. So we'll start the lectures by talking about the concept of a qubit and the concept of a quantum superposition, which is something that distinguishes a quantum bit or a qubit from just a classical bit of information. So classically, we know that the foundation of all computing is just a set of zeros and ones. So all the data in a computer program, for example, by binary representation of numbers, you can reduce it to sequences of zeros and ones. So a bit of information is something that can be 0 or 1. Now, so if you think about maybe physically storing that information, so for example, a magnetic hard drive, then there are sectors on this hard drive, and maybe in one sector, you have a net magnetization that's positive, and a different sector, you have a net magnetization that's negative. So one would assign maybe a 0 to this and a 1 to that. So then there's a one-to-one correspondence between some physical system in some state. So state of a physical system corresponds to 0 or 1. So the assumption is that that physical system can have two states that we can distinguish. And that's all fine. And then, if you have many sectors, you have lots of these bits. So that's the building block of classical computing. So you can represent the data that way. You can store the information in terms of these zeros and ones. And also the instructions can be compiled into zeros and ones. So that's a classical bit that can be just 0 or 1. Now, quantum mechanically, when we make these physical systems very small and very well isolated from a thermal environment, they behave in a very different manner. So they're not just going to be 0 and 1. We cannot write a consistent theory that describes all experimental observations by just saying, well, it's either positive or negative. So they behave that way, and we only have these two discrete states. Quantum mechanical systems behave differently. They behave in a probabilistic manner. So for example, suppose we make the physical system small and thermally isolated. So examples, a nuclear spin. So elementary particles have an intrinsic angular momentum, and that angular momentum for so-called spin 1/2 particles can take two possible states if you measure it in some direction. Let's say in the z direction, it can be either up or down. And suppose we want to store this two-level information that's 0 and 1 in something like that. Or you can think about maybe the polarization of a photon. Or we can think about a superconducting ring that's very well isolated from a thermal environment, and then maybe you have current going this way or that way. Again, these are examples of an effective two-level system, and if you make them very small and isolated, this classical picture that is either this or that, it's just a binary, is not going to work. It's not going to be able to explain experimental observations. So a quantum bit in general, let me just first state the result. So we're saying a quantum bit, also known as a qubit, in general is going to be a superposition of these two possibilities. So I have some complex number alpha times something that's 0 plus another complex number beta times this one. So that's a general quantum state. Of a two-level system. Alpha, beta are complex numbers. And 0 and 1 are quantum states corresponding to observing 0 and 1. So for example, if I'm working with spin and I measure it and I find it to be up, right after that measurement, I can assign a state 0 to that system. And if I measure the spin and I find it to be down, right after the measurement, I can assign this other state to my system. Okay. So the question is, what does it really mean when we say quantum state is some linear combination of both, right? So if you think about flipping a coin, when it lands, it's either head or tail. So it's either one or the other. Or if you measure that spin, it's either up or down. Or if you look at the current in a loop, it's either going clockwise or counterclockwise. So what does it mean? Like that you have this state that's at least while you're not looking at it, is a combination or a superposition of both of these things, and we can have both of these states present. The classic example is something known as a Schrödinger cat. So this becomes really counterintuitive and strange if you think about these zeros and ones corresponding to the states or the possibilities of a macroscopic, tangible, everyday big system. So Schrödinger, one of the pioneers of quantum mechanics, came up with this paradox of a cat that's in a box. You can't see the cat, and the cat can be dead or alive. And what does it mean that the cat's in a superposition? So is it at the same time in both states, and then there's some probability of finding the cat to be dead or alive when you open the box? So it's it's a very counterintuitive concept, but it turns out that systems that are isolated from a thermal environment experimentally behave like that. So let's try to build more intuition about what these things mean. So consider a scenario where we can prepare identical copies of the same quantum state. So let's do this thought experiment. So consider many identically prepared quantum states. So perhaps we can perform a measurement on a spin, finding it to be up, so they're all the same, and then we manipulate all of them in an identical way. Maybe you shine some light, you apply some magnetic field to each of those, and you make sure those magnetic fields are identical and they're applied for exactly the same time. So imagine a scenario where experimentally I can prepare many copies of this quantum system, and I've somehow guaranteed that they're all in the same state. They're all the same. So here I have n equal 7 of these copies. And psi, we're representing it by some superposition. So the motivation for this is the experimental fact that even if you apply this procedure, so you make a certain number of identical copies, and we know that they have the same state. And now suppose, so this is let's say before measurement. And then at a given time, I measure that quantity that can be 0 and 1, then can have 2 different values on all of these 2-level systems. So let us measure the 2-valued observable. So it turns out if you do that, even though these bits are supposed to be identical, you prepared them in exactly the same way. For some of them, after the measurement, we're going to find 0. For some of them, we're going to find 1. So, and that seems to be quite random and stochastic. It seems there's some probabilistic nature. There's no way to predetermine the result of the measurement for each and every 2-level system. So after the measurement, we have these states. So suppose I still have 7 of these, 1, 2, 3, 4, 5, 6, 7. And maybe this guy becomes 0. This one becomes 1. Maybe this is 1 again. Maybe this is 1 again. Maybe this is 0. This is 0, and that's 1. So I find different results. For some of them, I find 0. For some of them, I find 1, even though the states were the same. And that's an experimental observation. That's a description of the physical reality. So this is after measurement. So we are somehow forced to say that 0 and 1 were both somehow present in the state psi before the measurement, because sometimes when you you find 0. Sometimes when you measure, you find 1. And the mathematical way to describe this that gives a consistent theory is to write your state as a linear combination of these. Then we have to give some interpretation to these numbers alpha and beta, so they correspond again to some physical reality. So the way it works is that if we normalize our state, I'll explain in a second what that means. So what it means is that if I require that absolute value alpha squared plus absolute value beta squared is 1, then this is the probability of finding 0 when you perform a measurement in this state. And this is probability of finding 1. And these numbers add up to 1, so that makes sense. So then the sum of the probabilities of all possible outcomes is going to be 1. So this is known as the normalization condition. So a quantum superposition state can be viewed this way. It's a combination of the two states corresponding to these two possible outcomes of a measurement. This is really analogous to just representing points, for example, on a two-dimensional plane. So there's a geometric analogy that's pretty useful. So think of points on a two-dimensional plane. And we're familiar with this notion of picking a coordinate system, say the x and y, and then a given point, I can imagine there's a vector from the origin drawn to that point. So let's call that vector r. And we can always decompose that vector into, so imagine we have these unit vectors I and j in the x and y direction. So I can think of a decomposition of a vector in terms of these unit basis vectors. So let's write it as x if that component is x, and here suppose that component is y. So it's going to be xi plus yj. So for a point on a two-dimensional plane, x and y are real numbers. And then if I if, let's say, the length of that vector is 1, which is analogous to the normalization condition, then those points are going to be on a circle around the origin. And that's the set of all vectors that are normalized in 2D. So a quantum bit mathematically is very similar to this. So the two possible outcomes of measurement give two basis vectors, and the state can be viewed as a vector in some vector space. That's a combination of these two basis vectors, and in some sense the normalization condition says that the length of this vector is fixed to be 1. Now, there is one difference. So x and y here, when we're thinking about points on a plane, are real numbers. Quantum mechanics relies on having complex numbers. Essentially, the equation that governs the dynamics of a quantum state has an I in it. So we cannot get away from complex numbers in representing a quantum state in general. So we can view the quantum state as some vector of length 1 in a complex vector space, in some sense. Maybe at this point, I'll pause a little bit and very, very quickly review complex numbers, just so we have all the information. So a complex number, so review. Complex number Z has a real part, which we call X, and an imaginary part we call Y. So it's written as X plus I times Y. I is the so-called square root of -1. So we imagine I squared is 1. And we know that any real is -1 rather. We know that any real number squared is going to be non-negative, so I cannot belong to real numbers. So X is the real part of Z. Y is the imaginary part of Z. There's the notion of complex conjugation, which takes I to -I, changes the sign of I. And the notation for that is put in a star. So Z star is the complex conjugate of Z, and that's written as X minus I, Y. So X and Y are real. The complex conjugate of a real number is the same. This operation doesn't do anything to real numbers, and it changes that I to -I. And then the absolute value of a complex number is also defined as the square root of Z times Z star. So we can think of Z times Z star, which is the absolute value of Z squared, to be, let's just write it out, it's X plus IY, X minus IY. So that gives X times X is X squared. I times minus I is going to be -1, which is 1. So that gives me 1. Then I get a y squared. And then I have minus IXY plus IXY. So those cross terms cancel. Okay, so that's a brief review on complex numbers. All right, so let's continue with this discussion here. So what we're saying is that there is this interpretation in terms of probabilities of finding 0 and 1 if you have a particular state. So let's go back and also just get a better sense of what that means. So what the probability implies is that if you measure many qubits, so let's go back to that set of identically prepared qubits. They're all in state psi, which we represent as alpha times 0 plus beta times 1. So that's pre-measurement. And let's say post, so let's say I have n qubits. And then post-measurement, again, some of them become Some of them become zeros, some of them become ones. So suppose I have n0 0 states and n1 1 states post measurement. And again, we're saying psi is alpha 0 plus beta 1. So what the probabilities mean is that for very large n, if I repeat that experiment many, many times, if I have a very large number of these identically prepared qubits, then essentially the limit of n0 over n when n goes to infinity is the probability of finding a 0, and that's going to be my alpha squared. And the limit of n1 over n when n goes to infinity is going to be my absolute value beta squared. All right. So one way to represent this state, in the same way that when we were representing, let's say, a vector with its components. So if you have a vector r, again, that length is x, that length is y, plus yj. We had this way of representing the vector by just its components. So we assume that we fix a coordinate system. And then if I just give you the two numbers x and y, I've told you what that vector is, right? Given that we have the convention of that fixed coordinate system in our mind. Similarly, for a state psi, which we write as alpha times 0 plus beta times 1. So that's a superposition of the two possible observables for a qubit. I can represent psi again by having in the back of our mind what the two basis vectors are, what are the two possible measurement outcomes and the states corresponding to them. I can represent this by two complex numbers, alpha and beta, and it's very common to write that as a column vector. So as a 2-by-1 matrix, if you wish. So I put alpha here, I have one column, two rows, alpha, beta. That's a very useful representation of the state. The state of a two-level quantum system in a fixed basis. So what that means is these zeros and ones are fixed. We know what they are. Maybe they correspond to spin up and spin down for a nuclear spin, or current moving clockwise or counterclockwise in a superconducting ring. Okay, so that's a very useful representation. So let's think a little bit more about alpha and beta. We can think about parameterizing them in a way that guarantees normalization. So again, normalization means absolute value alpha squared plus absolute value beta squared is 1. Right, so alpha and beta are two complex numbers, right? So there are 4 real numbers. Each of them has a real and an imaginary part. So in the most general case, we're gonna need 4 real numbers to parameterize alpha and beta. This is one constraint that should reduce that number by 1. So the most general normalized state of a two-level system or a qubit must have three real numbers in it. So there's a very nice way to do that. So let me write it, and then we'll talk a little bit about this. So an alternative representation that takes into account the normalization automatically is to write psi as e to the I gamma cosine theta over 2 times 0 plus e to the I phi sine theta over 2 times 1. So as you can see, we have three real numbers in it. We have gamma, theta, and phi. So, and we can check the normalization. So that means that alpha, if I read it off, is going to be e to the I gamma cosine theta over 2. And beta is going to be e to the I gamma e to the I phi sine theta over 2. Okay. So let me briefly also talk about what this means, like the complex exponential. So there is a very important relationship known as the Euler formula that says e to the I whatever, let's call it lambda for some real number, is cosine of lambda plus I sine of lambda. So in other words, the real part of e to the I lambda is cosine lambda, and the imaginary part of e to the I lambda is sine lambda. For any real lambda, that works. So one way to see this is maybe thinking about the Taylor expansion of both cosine and sine and an exponential, and using the fact that I squared is -1. And then collecting the terms that are complex that have an I left over, and collecting the terms that are real. Okay, so then the consequence of this is e to the I lambda absolute value is always 1. How do I know this? Well, I need to multiply that by its complex conjugate, right? So if z is e to the I lambda, then z star, the complex conjugate, is going to be, I just change I to minus I, so it's going to be e to the minus I lambda. Therefore, z times z star is going to be e to the I lambda minus I lambda, right? When you multiply exponentials, the exponents add up. So, and that's e to the 0, and that's 1. So e to the I lambda, something like this, is called the phase factor. So armed with this, it's going to be very easy to verify that this parameterization always gives a normalized state. So how do I think about this? Well, let's write alpha absolute value squared is going to be alpha times its complex conjugate, right? So it's going to be e to the I gamma cosine theta over 2 times e to the minus I gamma cosine theta over 2. So let me make that cosine squared theta over 2. E to the I gamma, e to the minus I gamma, they cancel out. So that's just cosine squared theta over 2. And similarly, beta squared, absolute value squared. Now, we have two of these. We have e to the I gamma, but when that multiplies its complex conjugate, it gives me 1. We have e to the I phi. When that multiplies its own complex conjugate, it gives me 1. So for a very similar reason, this is going to be sine squared theta over 2. And then alpha squared, absolute value, plus beta absolute value squared is going to be cosine squared theta over 2 plus sine squared theta over 2. And that's an important trig identity. So sine squared plus cosine squared is always 1. So this parameterization guarantees the normalized state. At this point, you may be asking, why did I call that theta over 2 instead of just theta? It seems that that's just a phase, right? So we'll talk about that interpretation a little bit later in the course. There is a physical interpretation, but at this point, let's not worry about that. Okay, so let's keep going a little bit. So there's also a very nice geometric way to represent the state. So we said a convenient parameterization is e to the I gamma cosine theta over 2 times 0 plus e to the I phi sine theta over 2 times 1. It turns out that an overall phase factor for a quantum state does not have important observable effects. So as you can see, it for sure doesn't change any probabilities. And you could also argue that, well, this e to the I phi also doesn't change the probabilities for 0 and 1. But it turns out if you perform measurements, so if you measure something else instead of these zeros and ones, or if you evolve the system in a way that mixes the states. So for example, an evolution that takes maybe 0 to 1 over square root 2 of 0 plus 1 and takes 1 to 1 over square root 2 of 0 minus 1 or something like that. If you manipulate the system and let it evolve, the relative phases actually have important consequences. But this overall phase, it turns out is not important. So it's conventional to just drop it. So useful convention is setting gamma to 0. So we represent psi, the state of a general qubit, normalized state of a qubit in general, where we don't worry about the overall phase. We can represent it as just cosine theta over 2 times 0 plus e to the I phi sine theta over 2 times 1. So we use two real numbers to represent this state. In general, we had two complex numbers, but because it's normalized, that was one constraint, and because we don't care about the overall phase factor, that was another parameter that we threw out. So we have this 2-parameter representation of our state. So then it's going to be quite useful to geometrically represent that. So a very useful geometric representation is something called the block sphere. Essentially, these two angles can define a sphere. So let's say that's a sphere. Let's imagine a coordinate system. So let's say that's Z. This is X going this way. This is Y going this way. And suppose I pick a point on this circle. So let's say the angle with the Z-axis is theta. And if you project that on the XY plane, the angle of the projection with the X-axis is phi. Right, so that's the way essentially any point on this unit sphere would correspond to one of those states. So if I think about the state, so let me write the state again. So we're saying psi is cosine theta over 2. So let's also specify the range. So theta is going to be between 0 and pi. And phi, let's say, is between 0 and 2 pi. So theta can go from the North Pole to the South Pole. Phi can go all the way around. So that's 0 plus e to the I phi sine theta over 2 times 1. So for example, if theta is 0, then psi is just 0, right? That sine of 0 is 0, so it kills that one. And if theta is, let's say, pi, then cosine of pi over 2 is going to be 0. And we're going to get sine of pi over 2, that's 1. And then this e to the I phi in that case just becomes an overall phase vector. It's not going to be that important. So it's going to be the South Pole, right? So in this geometric representation, the state 0 would be over here. That's this point. And the state 1 would be over here. South Pole. And then arbitrary superpositions would correspond to different points on the sphere. So that gives us theta and phi, and the superposition is defined that way. So this way turns out to be very useful for thinking about two-level systems. All right, I think that's a good place to stop. So in the next lecture, we'll begin talking about systems of multiple qubits. So in this lecture, we just focused on one qubit and try to describe it and think about the superposition. Next time, we'll talk about having multiple qubits and how to represent the state for 2, 3, or more qubits. How does superposition work out there? And we'll introduce some mathematical machinery known as the tensor product. All right.